In the past few videos we discussed the term engineering stress, and we are continuing discussion on that. However, in this video we are concentrating on a new term, that is strain. Both stress and strain should go hand in hand, because you are going to study the relation between strain and stress and related topics in the next videos. So we need to start the discussion on strain in parallel with the discussion on stress. So what is a strain? In simple terms, rather than going into engineering terms, a strain is a change in shape or a change in dimension. So any change in a dimension, whenever there is a change in a dimension, there is always a strain. Excuse me. When we look in detail into this topic, we will see there are different terms developed for strains in different axes, or strains parallel to different axes. For example, there are lateral strains, there are longitudinal strains, there are radial strains, etc. But before going in detail, we need to understand what the term strain is. For example, if you have a body like this, and suppose you are applying a force on the body, and say for example you are applying a force, and what happens, usually you know what happens when you apply force to a body. If it is a deformable shape, or if it is a not a very hard material, it would elongate. If you are applying a force like this, it would probably elongate or change its shape like this. And this the rate of this change is called strain. It could be in this case it is happening along this axis. Say for example we can call this axis X, and in this case it is happening in this axis. However, when we study materials, or when we study deformations of bodies, we will need to assess when that happens, at what particular load. When it comes to engineering analysis, you need to analyze at what particular load that deformation starts, and at what particular load that the deformation reaches a maximum point, and at what load the body breaks, etc. So you need to consider a few terms when you understand the term strain. Now the universally accepted testing system or testing machine for strain analysis is a universal testing machine, which is usually used for testing the mechanical properties of material. It's called a UTS, universal testing system. And you can, what you basically do in a UTS is you will have a specimen, and it will be supported at either ends, or you will have a means to apply a load onto this specimen. So you apply a particular load, and you decide a length of the specimen in which you are conducting the analysis. Let's call this L, and you apply a particular load, and you will also have a recorder elsewhere that will measure the change in dimension. So for each load you apply, there will be an extension on this length. So say for example you apply a load of 100 kilonewton, then there occurs a change of, say for example you have a change of delta L here, then your strain is, usually strain is expressed as epsilon, the term epsilon. The strain is the change in dimension, which is delta L, over original dimension, which is L. So from this expression you can see both the numerator and denominator are the same quantities or similar unit quantities, and therefore strain will not have a unit. say for example, if this is measured in meter, then this is meter per meter. Although strain doesn't have a unit, because you can see meter and meter will get cancelled, and therefore it is a dimensionless quantity. However, we used to specify strain in meter per meter, or millimeter per millimeter, or centimeter per centimeter, etc. Because if your original length, or if your length over which you measure the strain is long, then there could be possible changes to the deformation. It won't be the same deformation on 1 meter length and 100 meter length. Therefore, it is always good practice to specify what unit you have used to measure the length. It is not only in the case of length, you can also measure change in radius, change in diameter, etc. for bodies. Whenever a body is applied by a force, you can see if you pull a rod, what will happen is the length of the rod increases, and at the same time the diameter of the rod decreases, or radius of the rod decreases, in which case you will have two strains. The length increases, and therefore there is a lateral strain, and the radius decreases, and therefore there is a radial strain. So there are different terms of strain as you go along. You will see as you go along this topic. Now, as I said, strain usually is a dimensionless quantity. However, we tend to specify it using a meter per meter, or a millimeter per millimeter, like that. Now, so there, I already mentioned that there is a lateral, longitudinal, radial, etc. different kind of strains, and you usually use a universal testing machine to analyze the strain. Now, this is up until now we were all talking about pulling forces or tensile forces. There can be a compressive force as well. So if you have a body like this, and you apply a force that compress the body, what will happen is the length or the dimension over which the force is acted, the length will decrease, or that dimension will decrease. This will be the final dimension. But at the same time, as you know, the volume cannot be changed. The material or the body itself will be the volume of the body will still be the same, and therefore if there is a contraction, or if there is a decrease in one dimension, there should be an increase in another dimension to compensate this decrease, so that the total volume of the body remains constant. So in every case, you can see if there is a contraction or an extension of one dimension, there will be the opposite of that change will be happening in another dimension. And when we analyze complex shapes, we will come to know that there are different expressions for strains along different axes. Now, the importance of strain is in mechanical engineering and engineering analysis is very, very significant. Whenever you design a component, or whenever you design select a material, it is always important to look at the properties of the material, and look at the strain stress relations of the material. To make things easy, we create a diagram to show the stress strain relation of these materials. Now, we tend to use this stress strain diagram for every materials, and you can see this is defined. Generally, this is defined for all the case for all materials, and we can use it for specific materials as and when we have the test data or the test results for it. Usually on the x-axis of a stress strain diagram, it will be strain. So your strain is shown on your x-axis, and on your y-axis you have strain is again usually let's say millimeter per millimeter, and you have a stress on your y-axis in excuse me, megapascals. Now, there are 4 regions in a stress strain diagram. You can see this up until here. This is one region from here till here, and from here till here you have your region 2. This is 1 and that is 2, and from here till the top position of this curve you have your third region. So you have from here to here you have your region 3, and from here to the tip of the curve you have your region 4. Now the first region is called linear elastic region. Second is called yield plateau. Yield plateau. And third is called strain hardening region. And the fourth is called strain softening. So these are the 4 states in a stress strain diagram. Now the first region, as the name suggests, it's linear elastic. So whenever you pull or push a body using a particular force in the linear elastic region, the body will just continue to extend or continue to elongate. As if you have a body like this, and if it's a tensile force, tensile pulling force you are applying, the body will just extend, elongate in the linear elastic region. And as you can see, it is a straight line here, and therefore the change in dimension with the applied stress or applied force will be linear. There is, as you increase the force, there will be more strain. And then you have the yield plateau. Yield plateau is the region where the strain at initiation of hardening strain, or the strain is getting hardened in the yield plateau region, and that starts at the beginning point here. Sorry, the end point here, the strain hardening. It is not very clear where actually this point will occur. So once you reach your elastic limit, or once you finish the linear elastic point, there will be a sudden increase in strain with the applied force, and then at the end of that yield plateau you will see a dip in the stress, or a dip in the stress for the same strain, and then all of a sudden the material will start to strain harden, or there will be further increase in stress needed to create any further deformation in the material. So initially you have a linear region where strain increases with increased application of load, and then there will be a sudden increase of strain with the same load. You don't have to increase any load, but you will still have a yield plateau where you have a increase in strain with the same load, and then at the end of the yield plateau you have strain hardening, which means you will need to increase the stress further to make any dimensional change or any deformation in the body. And once you reach the top of the strain hardening point, you will start to soften the strain, which means with lesser and lesser stress you will see the body is getting elongated. So what happens is, initially you will have a shape. Say for example, if you have a shape like this, and you apply a force, and at the linear elastic region the body will just elongate with the increase in length and a slight decrease in radius or thickness. And as soon as you finish the linear elastic region, you will see in the region 2 you will see a sudden increase in strain. So as soon as you finish the linear elastic region, you will see the strain is increased all of a sudden. And then you will see strain hardening, which means further strain will only occur with the increased stress. So there at that point you will start to see a slight deformation somewhere in the body, and we know that we will know from further studies that there are other factors that will cause the deformation in the body at particular points. There are numerous factors that will affect where this dimensional change actually occur, and once you reach this is where the strain hardening occurs, in which case you will need more force, or you will need more stress to create this strain hardening. And then once it started strain hardening, it will with the same or lesser amount of stress, the body will just go with the further deformation, and eventually that will, not getting my lines straight. So in all cases you are applying a force, and eventually the body will, if it's a rod or if it's a plate, it will break here, and you will have two cracked ends once the body is reaching its ultimate load point. So this happens over the point, over these different areas. Initially you will have a linear relation between stress and strain, and then all of a sudden your strain increases with the constant application of stress. Then it's strain hardening, and at which point the body starts to deform or reduce its dimensions, and it is about to form a dimension where it potentially will crack later on, and after the strain hardening region it will soften, and with any even with the same stress, the body will increase its strain and eventually break at this point. So you have four regions: linear elastic, yield plateau, strain hardening, and strain softening in a stress strain diagram. We will see different stress strain diagrams or stress strain diagrams for different materials in the following videos, and we will also see the relation between stress and strain in the next videos. Thank you.